This is the third and last lecture from Chapter 15. I see up here I still have it written as Chapter 14. It's really Chapter 15. And this lecture is about how to predict equilibrium concentrations when you do not know them using something we call an ICE table. So you know how to set up an equilibrium expression. K is concentration of products over concentrations of reactants raised to whatever their coefficients are in the balanced reaction. And so you know if you're given equilibrium concentrations of reactants and products, it's simply a plug and chug type of problem. So for example, let's say you're given a reversible reaction and you're given equilibrium quantities and asked to calculate the equilibrium constant. Go ahead and just make sure you can do that. Make sure you know the basics. It's worth kind of forcing yourself to get through that. There are a couple of minor pitfalls in the wording here that I want to make sure you can catch, and then compare your answer to the one I show on the next page. All right, so first of all, did you remember to convert the moles of the reactants and products into molarity, moles per liter? And did you get all of your exponents correct? If you did so, then you should have gotten an equilibrium constant equal to 1.08 times 10 to the 7th. That's just kind of a quick refresher for the easy multiple choice type plug and chug equilibrium constant. Now let's move on to the not so easy calculations of equilibrium constant. So what if you have a problem that rather than giving you equilibrium concentrations, it gives you initial concentrations and you have to figure out what they are? Well, back to the ICE table. The I stands for initial concentration. C stands for the change in concentration in going from initial to equilibrium. And E is, of course, equilibrium concentrations. You need to do these for reactants and products. So the best way to teach this is simply just to show you examples. The key to working successfully with an ICE table is to understand what the change row is for, right in the middle. So it's pretty self-apparent what initial concentrations are, whatever they happen to give you. I will point out at this time that if you are, unless you're told otherwise, you assume the initial concentration of products is 0. That's normally the case when you're doing a reaction, again, unless you're told otherwise. And so the change, the relative change depends on the coefficients in the balanced reaction. So if you say that the change in concentration for nitrogen, for example, in this reaction is X, and of course, since it's a reactant, it'll be decreasing, mathematical signs matter here, then the change in concentration of hydrogen for this reaction would be minus 3x, because for every one nitrogen that disappears, 3 hydrogens disappear. And then going along the same lines, the change in concentration for the product ammonia would be plus 2x. All right, so mathematical signs as well as coefficients for the balanced reaction are important. Once you have the change predicted, you can get all the equilibrium concentrations. So here's an example, very simple reaction. In this case, you're given K, but you always want to write the expression for K out before you start your ICE table. I can't tell you the number of students who forget to write out this simple expression, do all the sophisticated work on the ICE table, and then because they don't have K expression written correctly, miss the problem. So take the time, plus it's worth some partial credit, and write out the equilibrium constant expression. Okay, set up your ICE table I usually just write the reaction at the top of the ice table. Works out real well for making my columns. Alrighty, so the initial concentration of bromine is 0.063 molar, and the initial concentration of bromine atom is 0.012. So in order to get to the concentration equilibrium, we have to use X. So we're going to call the change in concentration of molecular bromine minus X. It's a reactant, so it's decreasing. And bromine atom product is increasing, so there's a plus sign, and it also has a coefficient of 2. Now you simply treat it like an addition or subtraction problem. So the equilibrium concentration of molecular bromine is the initial concentration minus X, and the equilibrium concentration of the bromine atom is, again, the initial concentration plus 2X. Now you take these equilibrium values and you plug them as they are back into the expression for the equilibrium constant. All right, so let's just rewrite the expression. Here is concentration of the bromine, the product, squared. Again, after doing all this hard work, don't forget the exponents. And concentration of the reactant, the bromine, molecular bromine here. They gave us the value for K, and now you have to solve for X. So you've got to be up on your algebra skills. I would go ahead and instead of looking at this answer right now, focus on this equation and see if you're able to simplify it and solve for X. Remember the quadratic formula. I will not give you problems that require use of the quadratic formula on my unit exam. However, I've been told by former students that there are 2 to 3 questions on the ACS final exam that do require you to use it. So you will want to know the quadratic formula. You will need practice with it, okay? So once you have simplified the equation and you have it in the form of a binomial, an x squared term, an x term, and then just a non-x term, and you set it equal to 0, then you can use the quadratic formula, solve for x, and as always, you get 2 possible values of x. It will turn out that one of these values is impossible and the other one works. So you're not quite done with your work yet. Let's look at both of these values and see which is the real value. All right, so realize that solving for x doesn't necessarily answer the question. The question asked you, what is the equilibrium concentration of the reactants and products? So you're not done when you find x. You have to go back and plug x into these equilibrium concentrations. So let's do the product, the atomic bromine first. 0.012, okay, plus 2x. So there are 2 possible values of 2x. Alrighty, so the 2 values of x that we came up with on the previous slide, I just jotted them down here. So if you try the first one, so 0.012 minus 2x. So if we have x equal to 0.0105 and then multiply that by 2, we come up with 0.0210, okay? Now, that's going to give you a minus value for concentration, which is impossible, all right? So this 0.0105 value for x is impossible. That simplifies our work. So the actual, when we subtract 0.012 minus 2 times this other value of x, we get that the equilibrium concentration of bromine atom is 0.00844. Now, since we know what value of x is correct, we can find the equilibrium concentration of molecular bromine. And it is 0.063 minus x, which we've determined is 0.00178. and that gives us an equilibrium concentration for molecular bromine of 0.0648. Alrighty, here is a different one which requires an ice table. If you're feeling particularly confident, try this on your own, even if you slaughter it, okay? You'll learn faster and better that way. If you're still totally lost, hang with me and I will walk you through this one too. All right, so in this case, our reactant is hydrogen iodide, and they gave us a piece of information. Instead of giving us the equilibrium constant value K, they give us one of the equilibrium values. So it's going to be a little bit different. Still, the first thing you should do is write out the expression for K. So that is concentration of the products raised to their coefficient, which happens to be 1 for each of them, and then over concentration of reactant, and that would be squared because of this 2. All right, so we don't know the value of K, but I'm going to go ahead and set up our ice table. I also want to point out to you, just be on the alert that the starting amount was not given in concentration, so you're going to need to calculate that first. So 1 mole divided by 10 liters, so the initial concentration of hydrogen iodide is 0.1 molar. So here's our ice table. Again, I always start by writing the reaction on the top and filling in all the information the problem gave us. We start with a starting concentration of 0.10. Remember I said to assume the concentration of the product in the beginning is 0. And before you start using X's, anytime they give you an equilibrium concentration of one of the components, you don't really need to use X. You can if you want, but now you can get the actual number that X is. So you know that whatever the change is here for iodide, the initial plus the change have to add up to be equilibrium. So the change has to be 0.020. So now once you have any of the change values, you can find the rest of them, because remember they all depend on the coefficients in the balanced reaction. So iodine and hydrogen both have a coefficient of 1 in the balanced reaction. So the change for hydrogen is also plus 0.020. So that means the equilibrium concentration of hydrogen is 0.020. All right, so now what is the change for hydrogen iodide? It's 2 times 0.020, okay? But now there is a minus sign, okay, because it's decreasing in concentration, it's the reactant. All right, so now what is the equilibrium concentration of hydrogen iodide? It's the initial concentration minus the change, which is 0.040. And so the equilibrium concentration of hydrogen iodide is 0.060. So now you can go back, plug into the expression for KEQ, and solve. So here we go. We're going to plug back into the equilibrium expression. Don't forget to square. And then we get that the equilibrium constant value is 0.11. Now, this one you definitely need to try on your own. So go ahead and pause the video and see how you work it out, and then check your answer in the next slide. Just a checkpoint here. Make doubly, triply sure that the chemical equation you're working with is balanced. This one is, but just double check on any type of test or quiz that it is in fact balanced. Go ahead, once you have the balanced equation written up, and set up your ice table and put in the given information. They told you the 2 initial concentrations of reactants. You're going to assume the concentration of the product is 0. All of these reactants and products have a coefficient of 1 in front of them. So the reactants are minus x, the product is plus x. Now you have your expressions for equilibrium concentrations, and you're going to plug those values into the equilibrium constant expression, which is right here. Alrighty, so they gave you the equilibrium constant, and you will always, even when you use an ice table, you'll be given either the value of K or the value of one of the equilibrium constants. So there are two basic types of problems. All right, so here's your values. Again, I hope you force yourself to multiply this out, get it in a quadratic formula, and solve for x. So your equilibrium concentrations are as follows. And once again, you will have two possible values of x, but one of those values of x will give you nonsensical values for equilibrium concentrations. You cannot have a negative concentration. So the value of x in this case that is correct is 0.0018. If you had all the time in the world, you may want to check that the value you got for x is correct. And how you would do that is you would take your equilibrium expression and you would plug in the equilibrium concentrations that you just calculated using your ice table and calculate the K. Now if you remember, originally in the problem they said that K was equal to 0.50, and you used that to solve for x. So now this is just kind of going backwards to make sure you didn't make a silly math error, and 0.49 is certainly close enough to 0.5. So it looks like you did your math correctly. All right, now, what is far more common than using the quadratic, and the only type of problem you will see on my exam, is using an ice table that allows you to make some simplifying assumptions about x, so that because of those assumptions you will not have to use the quadratic equation. And basically that happens when the equilibrium constant is very, very small. What that means, if K is very small, that means that reaction's not occurring very much. So let's look at this reaction. If K is small, that means there's not very much of the product, right? And if there's not very much of that product, you'll see in the next example that X can often be neglected. In other words, that the initial concentration can often be assumed to be the same as the final concentration. So this is a perfect example of a time when it's okay to neglect x. Look at this value of Kp. 9.3 times 10 to the minus 7. That's tremendously small. Okay, that means that the amount of product formed is almost negligible. And so it's likely when you see a Kp value that small, and the rule of thumb is that if it's 10 to the minus 3 or smaller, a little iffy if it's actually 10 to the minus 3, but certainly if it's 10 to the minus 4 or smaller, it's pretty safe to neglect x. All right, so let's take a further look at this example. If you set up your ice table, okay, reactant versus product, the initial concentration of reactant is 3 atmosphere. Well, it's in terms of pressure. And the initial pressure of the product is 0. Set up your expression for Kp. Remember, P stands for pressure. You do just like you do with concentrations, only you're going to use a P instead of brackets, meaning pressure. So pressure of N2O4 over pressure of NO, that should be NO2, squared because there's a coefficient of 2 here. Now, you would go ahead and plug into the equation for the equilibrium expression, and if you multiplied out to solve for x, you would get need to use a quadratic formula. However, keep in mind how very, very small the equilibrium constant is, which means x is very, very small, okay? It means there's not very much x form. There's not very much product form. And so anytime you see x in any form added or subtracted to some existing amount, you can neglect the x part of it, okay? So you started with 3 atmospheres, and since x is so small, because k is so small, 2x is going to be negligible compared to 3. So we're going to just cross out that minus 2x, and that dramatically simplifies solving. Now, you may say, well, can I just get rid of this x? No, because that would mean 0 in the numerator, and you get nonsense for a solution. All right, so kind of blow it up again. Take out this x value, and you get something that looks like this, and now much easier to solve for x, which ends up being 8.4 times 10 to the minus 6. So kind of ask yourself, if you neglected x and then you solve for it, it better be pretty small. This is very small. If it's not, you may have made an incorrect assumption. Now, this is kind of an obscure rule, but again, I've seen the ACS final ask about it. So if you're ever in question of whether it's okay to neglect x, we use something called the 5% rule to tell whether or not it's okay. And basically, you take x as a percentage of the original concentration or pressure that you subtracted it from, and you see if that ratio is less than 5%, it's okay to neglect x. Okay, so here we have, let's see, we solved for x, found it was 8.4 times 10 to the minus 6. We're going to compare it to the value we would have subtracted it from, which is 3. And it's a percentage. So we're going to calculate that. And it turns out that it's way less than 5%. As a matter of fact, that is 0.00028%. So it's really okay that we neglected the x here. And that is it for Chapter 15. Please don't minimize. If this seems understandable to you, that's awesome. That's a good start. But please try to work every single worksheet in the practice folder because there are so many different ways to ask these questions. And it comes down to old-fashioned word problems, whether or not you can understand what they're asking for and how to solve it.